All right, we're back with assumption number 2. Last time we saw that Niels Bohr, when he was attacking this problem of the weird spectrum of hydrogen with these 4 distinct wavelengths, he was looking at a new model of the hydrogen atom. And his first assumption was that the orbit is circular, as I've drawn here, and that the proton and the electron are attracted through the Coulomb force, the electrostatic force, the force that we dealt with way back first thing in chapter 15. 2 charged particles, unlike, attract each other to this Coulomb force. Okay, the Coulomb law. So, the second assumption complicates things a bit. Remember before, last video, video number 3, we talked about that first assumption. I drew the electron like it was a little point, right? I drew it like this. Like it was a little planet going around the sun. But we just said a few videos ago that that is not correct. Okay, Bohr picked up on this whole idea of de Broglie's that an electron should not only be thought of as a particle, it should be thought of in many situations like a wave. Remember, the particle-wave duality applies not just to light, but to stuff. An electron is stuff. So it's not just a little BB like this or a little planet orbiting, the sun of the nucleus. It's actually a wave going around. So imagine, instead of a single point particle moving around, imagine a wave spread out going around the circle, a wave going around this orbit. How do you draw that? Well, that's hard to imagine. But one thing you don't want to happen, listen closely, attend well to my words. One thing you don't want to happen as this wave travels around the circle, you don't want this wave to interfere destructively with itself. How is that possible? Well, you take a string, attach it to the wall, and start shaking a wave going down the wave. That wave is going to reflect and come back and interfere with itself. There's no wall in this case. It's going around a loop instead of down a string and back up the same string. It's going around a loop. What you need to have is you need to have the wave interfere constructively with itself, not destructively. If it interferes destructively, then the particle, the electron, whatever it is, the wave disappears. And you can't have it. So you got to have constructive interference. The wave has got to constructively interfere with itself. Which means that the circumference of the circle must be an integer number of wavelengths. So for example, if the circumference of the circle is 1 de Broglie wavelength, then it'll look something like this. Let's pick a good color for the wave itself. What do I have? Maybe yellow. This is hard to see, but if you have a wavelength, sort of like this. Actually, let's just do it like this. It's kind of hard to picture. I'm going to come flat out and admit that to you right now. Suppose we have a line like this, and we put one wavelength on it, like that. And now we take the original pink line and circle it back on itself to make a circle. Then the wave would look something like this. For the first half of it, it'd be above it, and then the second half would be sort of below it like that. So this is the orbit. The pink rather, is the orbit, but the yellow is the wave. This wave is interfering constructively with itself. It meets back up with itself nicely so that peaks meet with peaks and troughs meet with troughs, if we have a single wavelength. If we had two wavelengths, it would look like that. Now if we take that, how am I going to do this? How am I going to do this? Let's see. If we take that and map it onto our circle, if we take now this pink line and wrap it back around itself, now the circumference of that pink circle equals two wavelengths, right? This one here was one wavelength. Now this is two wavelengths. Now we take that pink line, wrap it back on itself. Here's the pink line wrapped around on itself. Now the wave looks something like that. And two, there's the peak, there's the trough, there's the peak, there's the trough. There's the peak, trough, peak, trough, peak, trough, peak, trough. So in that case, C is equal to 2 lambda. Finally, I'll stop at 3, but I will do 3. If we now take 3 wavelengths and fit them in, like that, now our picture looks like this. Oops, I didn't mean to erase my proton, but I did. Here's the pink line. Now, this case of fitting 3 wavelengths, now we take this 3 wavelengths, and now we again take this and loop it back on itself, take both ends of the pink line and bend them into a circle and let the yellow lines follow along. What we get, see if I can do this. Let's see, this should be fun. Something like that, 1, 2, 3 wavelengths. So this is circumference equals 3 wavelengths. Now what Bohr did was assume that this is the kind of thing the wave had to do. If this is the case, if C equaled some integer number of wavelengths where n equals 1, 2, 3, and on, because I can do this also with 4 wavelengths and 5 and 17 and 28. I just did the simplest ones, 1, 2, and 3. That's all. If I apply this, okay, then we can have any number, okay? And this was the assumption that he made, that an integer number of wavelengths fits into the circumference. Okay. That was the third assumption. And I'll let me see what we have at the time. I'll stop now and leave it. I'll leave you with this. We'll pick up with this formula right here next time, and we'll move forward with this assumption. And also, I will hit assumption number 3, and we'll finish out assumption number 2 in the next video, and in the next video we will finish out assumption 3, and then we'll put them all together.